Welcome. Today we are going to look into the various properties of natural gas and their estimation methods. Now, as we know that the properties play a very important role in any system because they determine the way a system would behave, and with the help of the properties we can analyze the system as well as we can design any kind of process. So it is very important for us to know the various types of properties, and you know that there are so many properties which determine or characterize a particular system behavior, but it is not feasible for us to list out all the properties. We shall be looking into some of the significant ones which are generally used for the analysis and the design of the various processes. And whatever I shall be talking to you about the properties, please keep in mind that the research is ongoing to estimate the various properties, and especially in case of natural gases, the task becomes still more complicated because the natural gas comes with so many types, with so many variations in the type of components, so many variations in the composition, that it becomes infeasible at times to give a generalized correlation or some equation to estimate the properties of all types of natural gas. So the research is ongoing till now to take up different types of natural gases and to develop different types of correlations based on the previous data and also based on the new observations. So in this regard, what I have done that I have divided my lecture of the properties into two parts. So today we shall be looking into the first part of the lecture on the thermophysical properties of natural gas. Now, in this particular lecture, we shall be learning about the various types of thermophysical properties, and under this we shall look into the gas specific gravity and pseudo critical properties, and we shall see how to estimate these two types of properties. Now, first let us see that what are the classifications of the various types of properties of natural gas. The classification first is the thermophysical property, and then thermodynamic property, chemical property, and combustion property. So, thermophysical property, it means that those properties which are dependent on the temperature, that is the thermodynamics, thermophysical properties, and they also include some of the physical properties also, about which we shall learn later. Here under this we have gas specific gravity, the compressibility factor, boiling point, freezing point, density, etc. Similarly, we have thermodynamic properties, under which those properties which are necessary for understanding and studying the energy transfer. There we have the thermal conductivity, specific heat, heat of vaporization, heat of fusion, heat of sublimation, etc. Then we have the chemical properties. This is especially true for the natural gas, because natural gas have many components which may be reactive, which may be soluble to other liquids. So here we have the reactivity, solubility, and hydrogen bonding, which is not a property in itself, but it dictates many of the properties of substances. Especially we know that in case of water, this bonding plays a very significant role. And lastly, we have another property which is unique to natural gas and oil, that is the combustion properties, because they determine the type of the natural gas, in the sense that how much energy we may be able to derive by the combustion of the natural gas or the oil. So these are related to the calorific value, and there is something another parameter, that is the Wob index and the ignition point, etc. So first let us go into the physical properties of natural gas. It has been found that natural gas is colorless, odorless, and non-toxic and lighter than air. When we say non-toxic, of course it means that generally it is under normal conditions, if we take it, it will not be causing any kind of problem, unlike carbon monoxide or carbon dioxide. And lighter than air means it will be always be, if there is any kind of leak, it will move up the air and it will get dispersed. So that is the meaning of the significance of lighter than air. Since natural gas contains several components, so as I told you that its property would be varying with the composition of the natural gas. Hence, we find the natural gases which are there in the different reservoirs the world over will be showing different types of characteristics and behavior when they are handled for the various type of processing we do with the natural gas. The properties are estimated by using some appropriate mixing rule. Mixing rule, why we need mixing rule? Because we might be knowing the properties of the individual components of the natural gas, but when we want to find the average property of the natural gas, we need a appropriate mixing rule, and we have to understand the mixing rule is not a very simple job, because there are, again we have to figure out that what kind of mixing rules will be appropriate under certain conditions, and several researchers in the world over are working on the evolving mixing rule if the existing ones do not apply. So this is very important to know that mixing rules have to be appropriately chosen to find out the overall property of the natural gas. Now let us see that why means some significance of the properties. Like for example, we come to compressibility factor. Perhaps you will know about it, and we shall learn about it also. That this compressibility factor is used to find out the density, viscosity, and again this density, viscosity dictate the flow characteristics. For example, you know that Reynolds number has both the density and the viscosity in it. So it determines the type of flow we shall be having in a pipeline, and how much will be the resistance to the flow into the pipeline, that is determined by the viscosity. So and these quantities, density, viscosity, they are obtained from the compressibility factor. And again, density and viscosity themselves are determining the type of flow and also the compressor power. That means if we are using any kind of pump or compressor, then how much power is required to make the flow happen will also be determined by the density and the viscosity. Next, we look into heat capacity and thermal conductivity. We know that heat capacity is the amount of energy needed to change the temperature by a degree per unit mass of the particular substance. That is the heat capacity. So how much, and that also signifies the time, or how easy or how difficult it will be to change the temperature of a particular substance. That is the significance of the heat capacity. Means how much energy it can retain inside itself is the heat capacity. And thermal conductivity signifies that how fast the energy can be conducted from one location to the other. So that is the significance of the thermal conductivity. And these two properties dictate that whenever there is a kind of flow inside any pipeline or any kind of system equipment, then these two properties determine that how much energy will be stored by the particular substance, as well as how this energy will get dispersed into the system. And this energy dispersion, as we know, they dictate the temperature distribution inside a system. So this is very important for us to know that whether the particular system is going to cool down or whether it is going to heat it up. So all these characteristics are dictated by heat capacity, thermal conductivity, in addition to the type of flow. Okay. So if you look into the energy balance equation, you will find there is some convective term, there is some conductive term. The convective term comes due to the flow of the system. So in case of flowing fluid, this both the conductivity, specific heat, in addition to the density, viscosity, will determine the distribution of the energy, which in turn will be reflected in terms of the temperature profile inside the system. So that is why it is also important for us to know how to obtain the values of the heat capacity and the thermal conductivity. Next comes the calorific value, and as we know, this signifies the amount of energy that can be derived by combustion. For example, in our home we are using LPG every day we are using LPG, and nowadays we are also getting LNG or CNG at our in some vehicles or for household uses. We find that all these LPG or LNG or CNG, whenever we are burning them every time, we are burning them and combusting them, and we are deriving the combustion in, energy, and sometimes we are using it to propel our various type of vehicles, or we are also using this energy for our cooking purpose. So this is very important for us to know that how much energy we can derive by combustion of these gases, and that is signified by the calorific value, and there is something called verb index, about which we shall be studying later. Now, here in this particular table, what I have shown is to just give you some idea about the thermophysical properties of the various components present in the natural gas. And here I started with methane because methane is the main component of the natural gas. Generally, it will be in a good reservoir, it will be above 80% or more. So, methane, this is chemical formula is CH4, and it is written like as C1. C1 components components, methane, and its molecular weight is 16. Critical pressure, critical temperature are also given here. So we find that all these components, methane, ethane, propane, isobutane, N-butane, isopentane, etc., they have been represented by different types of symbols. C1 for those hydrocarbons, we have only one carbon. Then C2 are those which have two carbons. C3 means those hydrocarbons which have 3 carbon, and similarly and so on, and each of them we find that they have different types of molecular weight and the critical pressure and critical temperature, and these values are necessary to find out the overall property of the natural gas. In this table again we find some other components like pentane, hexane, heptane, octane. Now we have stopped up to octane because we have to remember that natural gas cannot have too heavy hydrocarbons, because if heavy hydrocarbons are there in his system, then they will tend to go to the liquid phase rather than staying in the vapor phase. So natural gas generally contains up to C8 component, that is octane. And other components which are also present in natural gas are nitrogen, then carbon dioxide, hydrogen sulfide, and we showed in our previous lecture like norm, some kind of radioactive materials are also there in the natural gas. Now let us start seeing that how we estimate the property of natural gas. In this case, first I start with the gas specific gravity. Specific gravity, we already know that it represents the kind of a ratio between the density of a substance to the density of a standard substance. So people can use different types of standards. Somebody can use water as a standard. Generally we use water as standard. Sometimes for gases we use air as standard. So the gas specific gravity in case of natural gas is defined like this, the way we define it in general, that gamma g is the gas specific gravity and is defined as the density of the gas to the density of the air. We have to remember that when we talk of density of the gases, and because the gases are compressible, so their densities are a very strong function of both pressure and temperature. So whenever we are saying that the ratio of the density of gas to density of air, we have to understand that these refer to some specific temperature pressure. Okay, so with respect to that we talk, and here we show that how we can represent the density in terms of a compressibility factor. As I told you in the earlier slide, that this compressibility factor is a very important parameter to find out density and the viscosity. So here we find that we are representing the gas specific gravity in terms of the compressibility factor. So here this M represents the molecular weight and Z represents the compressibility factor. And at standard conditions, as you know, there are STP conditions, generally the compressibility factor of the gas and air are almost the same. So if these two Z's are same, then we can write this gas specific gravity simply as a ratio of the molecular weights, the ratio of the molecular weight of the gas to the molecular weight of the air. And perhaps you know that generally we take the molecular weight of air about 29. So this is the value we take, or 28.96 to be more specific. So this is the kind of value we take for the air, and we can find the gas specific gravity. Then we know that this, if I know the value of the specific gravity, then we know that how a gas would be behaving when it leaks. And leakage is very, we have to know the leakage behavior, because that has a direct bearing on the safety of the safety, because if some gas, some toxic gas is not dispersing well, it is settling down, like what happens in case of LPG, it may settle down because it's heavier than air. So it will have a direct safety issues on us. So it is important for us to know the gas specific gravity. Except methane, all hydrocarbons are denser than air. That because the natural gas is primarily methane, that is why generally natural gas is lighter than air. But if you look at LPG, which is basically isobutane and some amount of propane, so that is heavier than air. So if there is any kind of gas leakage from the gas cylinder at our home, then it will settle down rather than moving up. So that is the knowledge we gather from the gas specific gravity. So in case of natural gas leakage, we find the methane will get dispersed in the atmosphere, while the other components like ethane, propane, etc., they will tend to settle down. So methane will be going into the atmosphere. So it will move away from the point of leakage. Now next we come to another very important set of properties before we proceed to find out the other properties, reduced properties. Now why we need reduced properties? You know that whenever we are talking of any kind of density or other properties, there are so different components, we have different combinations of temperature, pressure, according to which we shall be having different property values. It becomes a mind-boggling affair to archive or to put all these, to develop any kind of database. So one way to ease out the representation of the properties is through these reduced properties. And what are reduced properties? Reduced properties represent the state variables of any fluid that are normalized by using the critical values of those variables. What is the meaning of the state variables? State variables are those variables which represent the state of a system. For example, we represent in terms of pressure, temperature, volume, etc. So these are state variables, and when we normalize them using their values at the critical point, we have the reduced values. So in that manner, we have here reduced temperature, we have reduced pressure, reduced volume, and so on and so forth. Now let us take one by one all of these. First we come to the general definition of reduced pressure and reduced temperature. Here first we have the reduced pressure. This reduced pressure, these values are given by a subscript R. So PR means reduced pressure. Similarly here TR means reduced temperature, and these are defined as the value, actual value to the critical value. So in case of reduced pressure, we have the ratio of the pressure to the critical pressure. Similarly, for the reduced temperature, we have the temperature divided by the critical temperature. Now, when we talk of a mixture of gases like natural gas, we do not have a single critical value. of any of the properties, because it has made several gases with it. Okay. So, in that case we have to figure out that how to represent the reduced values. To know that, we need to know how to have the reduced critical the overall critical values. So, first let us go to the definition that reduced properties is similar to the reduced properties, the pseudo reduced properties we define. Pseudo means it is not actual. There is a slight mistake in the spelling. It will be SE. So, it is pseudo reduced property, which means it is not actual, it is fictitious. So, this all sometimes they call it apparent. So, these pseudo reduced properties are defined in similar manner as reduced properties for the pure components, like the ratio of the value of state variable to their average the values at the critical points. So, similar to reduced temperature, reduced pressure, etc., we have the reduced we have the definitions for the various reduced properties, and these are the pseudo, this P for pseudo and R for reduced. So, pseudo reduced pressure, pseudo reduced temperature. This is defined as the pressure divided by the pseudo critical pressure, and then this is pseudo critical temperature. Now, there are various types of mixing rule, and very common mixing rule is given by K, and this K gives a mixing rule as the pseudo critical property as some kind of average, weighted average with respect to the mole fraction. So, this TPC is equal to summation of the product of the mole fraction and the critical temperature of each of the components. Similarly, the pseudo critical pressure is the summation of the product of the mole fraction and the critical pressure of each of the components. That is the mixing rule for pseudo critical temperature and pseudo critical pressure. Now, there is a very important principle, there is a principle of the corresponding states, which perhaps we know already. It says that at the same reduced temperature and reduced pressure, all properties become the same irrespective of the composition, and this way it makes our life easier to maintain the databases. So, if we know the reduced temperature, reduced pressure of various types of gas samples, we know that their reduced properties will also be the same. Now, before we go on to talk about these more, we see that how we represent these pseudo critical properties from the specific gravity if we do not know the composition of natural gas. Sometimes it may so happen we do not have the analysis, but we know what? We know the specific gravity. So, in these two equations we find the pseudo critical properties have been given in terms of the specific gravity. So, this will not need the knowledge of the composition of the natural gas. And there is another set of expressions for the pseudo critical pressure temperature that is given by Sutton, and this is another thing. But here you see there is a restriction on the value of the specific gravity. So, within this zone this particular expression may be used without knowing the actual composition of the gas. And also it is also important for us to know that these properties are affected by the presence of the non-hydrocarbons. So, here we have found people have proposed various types of correction factors. This prime represents the corrected pseudo critical temperature and the corrected pseudo critical pressure, and this epsilon is the correction factor which accounts for the presence of the carbon dioxide and the H2S, and this may be obtained graphically or from these following correlations, and in this correlation we find that the correction factor has been correlated with the mole fraction of carbon dioxide and the hydrogen sulfide. So, this expression may be used and incorporated here to correct the pseudo critical temperature and pseudo critical pressure. With this, we come to an end to this first part of the property estimation, and these are few of the references you may refer to for further understanding and analysis. Thank you.